What if everything you know about the universe is just a tiny piece of the puzzle? What if the cosmos we see, the stars, galaxies, and even the laws of physics are just one small corner of an infinitely larger reality? This isn't the setup for a science fiction story. It's a question that some of the brightest minds in physics are asking right now. The multiverse, the idea that our universe is just one of countless others, each with its own unique rules, has moved from the fringes of speculation to a serious topic of scientific debate. But how did this idea emerge, and why are scientists taking it seriously? In this video, we'll dive into the origins of the multiverse concept, the theories that support it, and the evidence that suggests it might not be as far-fetched as it sounds. Together, we'll explore what it could mean for our understanding of reality, and why the multiverse might be closer to science than fiction, ready to rethink everything you thought you knew. Let's begin. The idea of the multiverse isn't as new as you might think. In fact, its roots stretch back thousands of years, long before modern science even existed. Ancient philosophers like the Greeks and Hindus pondered the possibility of multiple worlds, imagining realms beyond our own where different realities might coexist. But it wasn't until the birth of modern physics that these speculative ideas began to take on a more concrete form. In the early 20th century, as scientists delved deeper into the mysteries of quantum mechanics and cosmology, the concept of a multiverse started to resurface not as philosophy, but as a potential scientific framework. One of the most pivotal moments came in the 1950s with physicist Hugh Everett and his groundbreaking many worlds interpretation of quantum mechanics. Everett proposed that every possible outcome of a quantum event actually happens, but in separate, branching universes. Think of it like this: every time you make a decision, whether it's something as simple as choosing a cup of coffee or as profound as changing careers, there's another version of you in another universe who made a different choice. It's a staggering idea, but one that offered a solution to some of the strange, counterintuitive behaviors of particles at the quantum level. But the multiverse didn't stop there. As cosmology advanced, scientists began to realize that our universe's laws, its constants, like the strength of gravity or the mass of an electron, seem oddly fine-tuned for life. If even one of these constants were slightly different, stars, planets, and life as we know it might never have formed. This led to a tantalizing question: could our universe be just one of many, each with its own unique set of physical laws? The multiverse emerged as a possible explanation for this fine-tuning problem, suggesting that in the vastness of existence, every possible combination of laws might exist somewhere. Today, the multiverse is more than just a theoretical curiosity. It's a serious topic of discussion among physicists, offering potential answers to some of the biggest unresolved questions in science. But how do we move from speculation to something more concrete? That's where the scientific frameworks come in. Theories like string theory, inflationary cosmology, and quantum mechanics all provide pathways to explore the multiverse. And as we'll see next, these frameworks aren't just abstract ideas, they're grounded in some of the most cutting-edge research happening right now. But how does something as abstract as quantum mechanics lead us to the idea of an infinite number of universes? To understand this, let's take a closer look at the many worlds interpretation, one of the most fascinating and controversial ideas in modern physics. Picture a tree with an infinite number of branches. Each branch represents a different outcome of a quantum event. When a particle has the potential to go left or right, spin up or down, or exist in multiple states at once, what physicists call superposition, the many worlds interpretation says it doesn't just choose one path. Instead, it takes all possible paths, each one creating a new universe where that outcome becomes reality. Imagine flipping a coin. In our world, it lands on heads. But according to this interpretation, there's another universe where it lands on tails, and another where it lands on its edge, and another where it never even leaves your hand. Every decision, no matter how small, creates a branching point leading to an ever-growing web of parallel realities. It's a mind-bending concept, but one that offers a unique solution to the strange behavior of particles in quantum experiments. Of course, not everyone is convinced. Critics of the many worlds interpretation argue that it's untestable after all. How could we ever observe these other universes? Renowned physicist Stephen Hawking once called it cheap on assumptions but expensive on universes, pointing out that it multiplies realities without providing a clear way to verify them. Others worry that it undermines the predictability of science, suggesting that every possible outcome happens somewhere, making it harder to pin down what's truly real. Yet, despite the controversy, the many worlds interpretation continues to captivate scientists and storytellers alike. It challenges us to rethink not just the nature of reality, but our place within it. If every choice spawns a new universe, what does that mean for free will, for destiny, for the idea of a single, unified you? These are questions that blur the line between physics and philosophy, and they're far from being settled. As we peel back the layers of the multiverse, another theory emerges, one that doesn't just suggest parallel realities, but entire universes with completely different physical laws. This is where inflationary cosmology comes into play, and it might just hold the key to understanding how the multiverse could be more than just a theoretical possibility. Inflationary cosmology, a theory that reshaped our understanding of the universe's earliest moments, takes the multiverse concept to a whole new level. The story begins in the early 1980s when physicist Alan Guth proposed a radical idea. What if the universe underwent an exponential expansion just moments after the Big Bang? This rapid expansion, called inflation, would explain why the universe appears so smooth and uniform on large scales. But as Guth and others dug deeper, they realized inflation might have an even more profound implication. It could have created not just one universe, but countless others. Here's how it works. During inflation, space itself expanded faster than the speed of light, stretching tiny quantum fluctuations into the seeds of galaxies and cosmic structures. But what if this expansion didn't stop everywhere at the same time? Imagine a pot of water boiling on a stove. As bubbles form and rise to the surface, each bubble represents a region where inflation has ended, creating a stable universe with its own set of physical laws. In this analogy, the boiling pot is the multiverse, a cosmic foam of bubble universes, each one isolated from the others, yet all born from the same inflationary process. This idea, further developed by physicist Andre Linde, is known as the inflationary multiverse. Linde suggested that inflation isn't a one-time event but an ongoing process. In some regions of space, inflation ends, forming a bubble universe, while in others, it continues indefinitely, spawning even more bubbles. Over time, this creates an infinite landscape of universes, each with its own unique properties. Some might have stronger gravity, others weaker nuclear forces, and some might even have entirely different dimensions. It's a staggering vision of reality, one where our universe is just one bubble in an unimaginably vast cosmic ocean. But how does this connect to what we can actually observe? The answer lies in the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light carries subtle imprints of the universe's infancy, and scientists have found patterns in it that align remarkably well with inflationary predictions. While we can't directly see other bubble universes, the evidence for inflation lends credibility to the idea that our universe might be part of a much larger multiverse. Critics, of course, raise valid questions. If these other universes are forever beyond our reach, how can we ever prove they exist? And if inflation creates an infinite number of universes, does that make the theory untestable? These are challenges that physicists continue to grapple with, but the inflationary multiverse remains one of the most compelling frameworks for understanding the cosmos and our place within it. As we piece together these ideas, one thing becomes clear: the multiverse isn't just a wild speculation. It's a natural extension of some of the most well-supported theories in physics. And if it's true, it would mean that the universe we call home is just one small chapter in an infinite cosmic story. But what does this mean for the laws of physics? Do they vary from universe to universe, or are they somehow tied together by a deeper, unifying principle? That's where string theory enters the conversation, and it might just offer the next piece of the puzzle. So, if the multiverse exists, how could we ever hope to find evidence of it? After all, by definition, other universes would be beyond our reach, separated from us by unimaginable distances or even entirely different dimensions. But here's the fascinating thing: scientists have been looking for clues not by trying to visit these other universes, but by searching for subtle fingerprints they might have left behind in our own. One of the most promising places to look is the cosmic microwave background, or CMB, the faint glow of light left over from the Big Bang. This ancient radiation is like a snapshot of the universe's infancy, and embedded within it are tiny irregularities or anomalies that might hold the key to uncovering a multiverse. Some of these anomalies are particularly intriguing. For example, in 2005, astronomers discovered a strange cold spot in the CMB, a region of space that's significantly cooler than its surroundings. At first, this might not sound like much, but when scientists like Stephen Feeney and his team analyzed it, they proposed a startling possibility. What if this cold spot is the imprint of a collision between our universe and another? Imagine two soap bubbles gently bumping into each other. The point of contact would leave a mark, and in the case of universes, that mark could manifest as a temperature anomaly in the CMB. It's a speculative idea, but one that's grounded in the mathematics of inflationary cosmology. Another clue comes from the work of physicist Laura Mersini-Horton, who has explored how quantum fluctuations in the early universe might have interacted with neighboring universes. She suggests that these interactions could have left specific patterns in the CMB patterns that we might be able to detect with increasingly precise measurements. While the evidence isn't conclusive, it's tantalizing to think that these faint signals could be echoes of a much larger cosmic reality. Of course, proving the existence of the multiverse is no easy task. The very nature of these other universes makes them inherently unobservable, at least with our current technology. Critics argue that without direct evidence, the multiverse remains in the realm of speculation. But here's the thing: science often progresses by looking for indirect evidence. Think of how we discovered black holes. For decades, they were purely theoretical, but by observing their effects on nearby stars and gas, we were able to confirm their existence. Could the multiverse follow a similar path? The search for evidence is ongoing, with new technologies and techniques constantly pushing the boundaries of what we can observe. From ultra-sensitive telescopes scanning the CMB to advanced simulations modeling the early universe, scientists are exploring every possible avenue. And while we may not have definitive proof yet, the very fact that we're asking these questions and finding potential hints shows just how far our understanding has come. But evidence isn't the only thing driving the multiverse idea. Beneath it all lies a powerful mathematical framework, one that ties together quantum mechanics, cosmology, and even string theory. To truly grasp why the multiverse is taken so seriously, we need to dive into the numbers, and that's where the story takes its next fascinating turn. If the multiverse feels like a concept ripped straight from the pages of science fiction, the mathematics behind it might just convince you otherwise. At its core, the idea of multiple universes isn't just a wild guess. It's grounded in some of the most sophisticated and elegant mathematical frameworks ever devised. Among these, string theory and its more advanced cousin, M-theory, stand out as key players in the multiverse narrative. These theories don't just suggest the existence of other universes, they demand it, painting a picture of reality that's far richer and more complex than we ever imagined. Let's start with string theory. At its heart, this theory proposes that the fundamental building blocks of the universe aren't point-like particles, as we've long thought, but tiny, vibrating strings. These strings oscillate at different frequencies, giving rise to everything from quarks to photons. But here's where things get truly mind-bending. For the math to work, string theory requires more than the 3 dimensions of space and 1 of time that we're familiar with. Instead, it suggests that the universe has 11 dimensions, 10 of space and 1 of time. Think of it like this. Imagine you're looking at a piece of paper. To you, it's a flat, 2-dimensional surface, but to an ant crawling on it, the paper is a vast, multidimensional landscape, full of folds and textures that you can't see from a distance. In the same way, the extra dimensions predicted by string theory are thought to be curled up or compactified, hidden from our view at scales so small we can't currently detect them. These compactified dimensions take the form of intricate geometric shapes known as Calabi-Yau manifolds, which look as though they've been plucked from the pages of an abstract art book. These manifolds aren't just mathematical curiosities, they're crucial to understanding how particles and forces might behave in a higher dimensional universe. But string theory doesn't stop there. When physicists expanded it into M-theory, they discovered something even more astonishing: the possibility of entire universes existing as membranes or branes floating in higher dimensional space. Imagine a loaf of bread where each slice represents a separate universe. In M-theory, these branes can collide, interact, or even stretch apart, creating a dynamic and interconnected multiverse. This isn't just theoretical speculation. The math suggests that such collisions could have even sparked events like the Big Bang, giving rise to our own universe. Of course, the elegance of these mathematical models comes with a catch. They're incredibly complex. Calabi-Yau manifolds, for example, are so intricate that even the most powerful supercomputers struggle to fully map their properties. And while the equations of string theory are breathtakingly beautiful, they're also notoriously difficult to solve. Some critics argue that this complexity makes the theory untestable, at least with our current technology. But for its proponents, the math is too compelling to ignore. It offers a unified framework that could explain not just the multiverse, but everything from the nature of gravity to the behavior of particles at the smallest scales. What's truly remarkable about these theories is how they bridge the gap between the abstract and the tangible. They take us from the realm of pure mathematics where dimensions curl and branes collide, to the very real possibility that our universe is just one of many. And as we'll see next, this idea doesn't just challenge our understanding of physics. It forces us to confront profound questions about existence, identity, and the nature of reality itself. Ready to dive deeper, let's explore what the multiverse might mean for philosophy and for us. The multiverse doesn't just challenge our understanding of physics, it forces us to grapple with some of the deepest questions about who we are and what it means to exist. If every possible version of reality exists somewhere out there, what does that mean for our sense of self, for our choices, for the very idea of free will? These aren't just abstract philosophical musings, they're questions that strike at the heart of what it means to be human. Take the concept of identity, for example. If the many worlds interpretation is correct, and every decision we make spawns a new universe, then somewhere out there is a version of you who made every possible choice. The you who became a doctor, the you who moved to another country, the you who stayed up late last night instead of going to bed early. All of these versions exist, each living out their own unique story. But if there are infinite versions of you, does that make you less unique? Or does it simply mean that individuality is more expansive than we ever imagined? This idea isn't entirely new. It echoes thought experiments like Schrödinger's cat, where a quantum event leaves a system in a superposition of states until it's observed. In the multiverse framework, the cat isn't just both alive and dead until we look. It's alive in one universe and dead in another. the act of observation doesn't collapse the possibilities into a single outcome. Instead, it branches reality into multiple paths. It's a strange and unsettling idea, but one that forces us to rethink the nature of existence itself. And then there's the question of free will. If every possible choice is made in some universe, does that mean our decisions are meaningless? Or does it simply mean that every choice matters because it defines the reality we experience? Some philosophers argue that the multiverse amplifies the significance of our actions. After all, if every path is taken, then the one we choose becomes the story we live. Others worry that it diminishes our sense of agency, suggesting that no matter what we do, another version of us is doing the opposite. These aren't easy questions to answer, and they've sparked debates that blur the line between science and philosophy. But perhaps the most profound implication of the multiverse is what it says about the nature of reality itself. If our universe is just one of an infinite number, each with its own set of physical laws, then the idea of a single objective truth starts to unravel. Instead, reality becomes a vast, interconnected tapestry where every thread tells a different story. As we wrestle with these ideas, it's worth remembering that the multiverse isn't just a scientific theory, it's a cultural phenomenon. From blockbuster movies to best-selling novels, the concept of parallel universes has captured the imagination of storytellers and audiences alike. And as we'll see next, the way the multiverse is portrayed in popular culture can tell us as much about our hopes and fears as it does about the science behind it. Ready to explore how the multiverse has shaped the stories we tell about ourselves? Let's dive in. The multiverse isn't just a playground for physicists, it's also a canvas for storytellers. Over the years, the idea of parallel universes has inspired some of the most iconic works in film, literature, and art. Take Marvel's Multiverse, for instance. In recent years, the Marvel Cinematic Universe has embraced the concept wholeheartedly, weaving it into blockbuster hits like Spider-Man, No Way Home, and Doctor Strange in the Multiverse of Madness. These films explore what happens when characters cross into alternate realities, meeting versions of themselves that are wildly different, heroes who became villains, or loved ones who never existed in their own worlds. It's a thrilling narrative device, but it also taps into something deeper, the universal human curiosity about paths not taken. What if you'd made a different choice? What if your life had taken a different turn? Marvel's Multiverse lets us explore these questions in a way that's both entertaining and thought-provoking. Then there's Everything Everywhere All at Once, a film that takes the multiverse concept and turns it into a deeply personal story. The movie follows Evelyn, a struggling laundromat owner, as she discovers that her mundane life is just one of countless versions of herself across the multiverse. Some versions are martial arts masters, others are chefs, and one is even a rock. Through her journey, the film explores themes of identity, family, and the weight of infinite possibilities. It's a brilliant blend of absurd humor and heartfelt emotion, showing how the multiverse can be used to tell stories that are as human as they are cosmic. What makes Everything Everywhere All at Once so compelling isn't just the spectacle of alternate realities, it's the way it uses those realities to reflect on the choices that define us. Of course, the multiverse isn't a new idea in storytelling. Classic science fiction has been playing with parallel worlds for decades. Think of Philip K. Dick's The Man in the High Castle, which imagines a world where the Axis powers won World War II, or consider Ursula K. Le Guin's The Lathe of Heaven, where a man's dreams can rewrite reality itself. These stories don't just entertain, they challenge us to think about the fragility of history and the consequences of our actions. In a way, they're not so different from the scientific multiverse theories we've been exploring. Both ask the same fundamental question: what if things had been different? But why does the multiverse resonate so deeply with audiences? One reason might be that it reflects our own anxieties and hopes. In a world that often feels chaotic and uncertain, the idea of infinite possibilities can be both comforting and terrifying. On one hand, it suggests that no matter what happens in this universe, there's another where things turned out better. On the other, it raises the unsettling possibility that our choices might not matter as much as we think. This tension between freedom and fate, between hope and despair, makes the multiverse a rich source of storytelling material. It's no wonder that filmmakers, writers, and artists keep coming back to it. Yet, for all its cultural appeal, the multiverse isn't without its critics. Some scientists argue that the concept has been oversimplified or misrepresented in popular media, turning a complex scientific idea into a convenient plot device. Others worry that the multiverse distracts from more pressing questions in physics, like understanding the nature of dark matter or unifying quantum mechanics with gravity. And then there's the question of testability. Can a theory that posits an infinite number of universes ever be truly scientific? These critiques remind us that, while the multiverse is a powerful idea, it's also one that demands careful scrutiny. As we'll see next, the scientific community is far from unanimous on whether the multiverse is a groundbreaking insight or an untestable speculation. But one thing is clear: whether in science or storytelling, the multiverse continues to captivate our imaginations. The multiverse may be a captivating idea, but it's not without its critics. One of the most common objections is that it's untestable and therefore, some argue, unscientific. After all, how can we prove the existence of something we can't observe or interact with? This concern has been raised by prominent physicists like Paul Steinhardt and Neil Turok, who have long been skeptical of the multiverse framework. Steinhardt, a leading figure in cosmology, has called the multiverse a theory of anything, suggesting that if you can explain every possible outcome by invoking infinite universes, you're not really explaining anything at all. It's a bit like saying there's an explanation for everything somewhere out there. While this might sound satisfying at first, it doesn't help us narrow down the specifics of our own universe or make concrete predictions. Another criticism is that the multiverse risks becoming a catch-all explanation for phenomena we don't yet understand. For example, the fine-tuning problem, the idea that our universe's physical constants seem perfectly calibrated for life, is often cited as evidence for a multiverse. But skeptics argue that this is just kicking the can down the road. Instead of explaining why these constants are what they are, the multiverse simply says, well, in some universes they're different. This doesn't provide a satisfying answer, it just shifts the question to a higher level. As Turok has pointed out, invoking an infinite number of universes to explain the peculiarities of our own feels like giving up on finding a deeper, more elegant solution. There's also the practical concern that the multiverse could stifle scientific progress. If we accept that every possible universe exists, does that mean we stop looking for simpler explanations? Some worry that the multiverse could become a crutch, allowing scientists to avoid tackling the hard questions by deferring to the idea that anything is possible somewhere. This isn't just an academic debate, it's a fundamental question about the direction of scientific inquiry. Should we aim for theories that are testable and falsifiable, or are we willing to entertain ideas that lie beyond the reach of empirical evidence? Despite these criticisms, the multiverse continues to be a powerful and thought-provoking concept. It challenges us to think bigger, to question our assumptions, and to explore the limits of what science can explain. But it also reminds us that not all questions have easy answers and that sometimes the most profound mysteries require us to consider alternatives. Speaking of which, let's turn our attention to some of those alternatives. What if the cosmic puzzles we're trying to solve don't require an infinite number of universes? What if there's a simpler, more elegant explanation waiting to be discovered? That's where we're headed next. While the multiverse offers a compelling explanation for some of the universe's deepest mysteries, it's not the only game in town. Scientists have proposed several alternative theories that aim to tackle the same questions, like why our universe seems so finely tuned for life, without resorting to the idea of infinite universes. One of the most intriguing of these is the Anthropic Principle. At its core, this principle suggests that the conditions we observe in our universe are the way they are because, well, we're here to observe them. In other words, if the constants of nature, like the strength of gravity or the mass of electrons, were even slightly different, life as we know it simply wouldn't exist. The Anthropic Principle doesn't try to explain why these constants are what they are. Instead, it frames the question in terms of selection bias. We live in a universe that allows for our existence, so of course it looks fine-tuned to us. It's a bit like finding yourself in a forest and wondering why the trees are just the right height to provide shade. It's not that the forest was designed for you, but rather that you're here because the forest happens to meet your needs. But the Anthropic Principle has its critics. Some argue that it's a bit of a cop-out, a way to sidestep the deeper question of why the universe is the way it is. Others point out that it doesn't actually solve the fine-tuning problem. It just reframes it. Still, it's a powerful reminder that our perspective as observers shapes how we interpret the cosmos. And it raises an interesting possibility. What if the fine-tuning we see isn't a sign of a multiverse, but simply a reflection of the fact that we're here to notice it at all? Another alternative worth exploring is cyclic cosmology, a theory that proposes the universe isn't a one-time event but part of an endless cycle of expansion and contraction. Imagine the universe as a cosmic accordion, breathing in and out over unimaginable spans of time. In this model, the Big Bang wasn't the beginning of everything, it was just the start of the latest cycle. Each cycle begins with a rapid expansion, followed by a gradual slowing and eventual collapse, only to rebound into another Big Bang. This idea, championed by physicists like Paul Steinhardt and Neil Turok, offers an elegant solution to the fine-tuning problem. Instead of invoking an infinite number of universes, it suggests that our universe has had countless practice runs, each one tweaking the constants of nature until they reach the values we see today. It's a fascinating idea, but it's not without its challenges. For one, we don't yet have a clear mechanism for how the universe could transition smoothly from collapse to rebirth without losing all its structure. And while cyclic cosmology avoids the need for a multiverse, it still relies on assumptions about the universe's behavior that are difficult to test. Then there's modified gravity, a theory that takes aim at one of the most puzzling aspects of modern physics, dark energy. This mysterious force is causing the universe to expand at an accelerating rate, but we still don't fully understand what it is or how it works. Modified gravity proposes that our understanding of gravity itself might be incomplete. Instead of invoking dark energy as a separate entity, this theory suggests that gravity behaves differently on cosmic scales than it does in our everyday experience. If true, this could explain the universe's accelerated expansion without needing to introduce dark energy, or by extension, the multiverse. Modified gravity has gained traction in recent years, but it's still a work in progress. While it offers a simpler explanation for some phenomena, it struggles to account for others, like the precise distribution of galaxies in the universe. And until we have more observational data, it's hard to say whether modified gravity is a viable alternative or just an intriguing possibility. Each of these alternatives, the Anthropic Principle, cyclic cosmology, and modified gravity, offers a different lens through which to view the universe's biggest questions. They remind us that science thrives on competing ideas, and that the multiverse, for all its allure, is just one piece of a much larger puzzle. But as we explore these alternatives, one thing becomes clear: the mystery of dark energy looms large. Could it hold the key to understanding not just our universe, but the multiverse as well? That's where our journey takes us next, as we dive into the enigmatic force that's shaping the cosmos on the grandest scales. Dark energy, a mysterious force driving the accelerated expansion of our universe, might hold the key to understanding not just our cosmos, but the multiverse itself. Discovered in the late 1990s, dark energy makes up about 70% of the universe's total energy content. Yet, despite its overwhelming presence, we know almost nothing about it. What we do know is that its density, the amount of dark energy per unit of space, is crucial to the universe's structure. If dark energy were even slightly more or less dense, the cosmos as we know it might not exist. This raises a fascinating question. Could variations in dark energy density explain why our universe has the properties it does, and hint at the existence of others? This is where physicists like Leonard Susskind and Raphael Bousso come in. They've proposed a groundbreaking idea that dark energy might not have a single fixed value, but instead exists in a range of possible densities across different universes. Picture a vast, rolling landscape where each hill and valley represents a unique configuration of dark energy. In some regions, the density is high, causing universes to expand so rapidly that stars and galaxies never form. In others, it's low, leading to a universe that collapses back on itself almost immediately. And somewhere in the middle, there's a sweet spot, a universe like ours, where the density is just right to allow galaxies, stars, and even life to emerge. This landscape of possibilities is more than just a metaphor. It's a framework that could explain why our universe seems so finely tuned for existence. Susskind and Bousso's work builds on string theory, which suggests that the extra dimensions we talked about earlier could give rise to an almost infinite variety of vacuum states, each one corresponding to a different density of dark energy. In this view, the multiverse isn't just a collection of random universes. It's a structured array of possibilities, each one governed by its own unique set of rules. Think of it like a cosmic lottery. Our universe happens to have the winning ticket, the precise combination of dark energy and physical constants that makes life possible. But what about the others? Could they be barren, lifeless expanses, or are they teeming with realities we can scarcely imagine? The concept of a landscape of universes is both elegant and humbling. It suggests that the multiverse isn't just a chaotic jumble of worlds, but a carefully balanced system where every variation has its place, yet it also raises profound questions. If our universe is just one of countless possibilities, what does that mean for our understanding of reality, and how can we ever hope to test such a theory? These are challenges that scientists are still grappling with, but the very fact that we're asking them shows just how far our understanding has come. As we delve deeper into the mysteries of dark energy and the multiverse, another piece of the puzzle comes into focus: black holes. These enigmatic objects, once thought to be the end of the road for matter and energy, might actually hold clues to the nature of the multiverse itself. From their event horizons to their singularities, black holes are more than just cosmic vacuum cleaners. They're windows into the fabric of reality. And as we'll see next, they could be the key to unlocking some of the universe's deepest secrets. Black holes have long fascinated scientists and storytellers alike, often depicted as cosmic monsters devouring everything in their path. But what if these enigmatic objects are more than just destroyers? What if they're gateways, portals to other universes? This idea might sound like science fiction, but it's rooted in some of the most cutting-edge theories in physics, including the ER=EPR conjecture. Proposed by physicists Leonard Susskind and Juan Maldacena, this theory suggests a profound connection between black holes and the fabric of spacetime itself. At its heart, ER=EPR proposes that two seemingly unrelated concepts, wormholes and quantum entanglement, are actually two sides of the same coin. Here's how it works. Wormholes, or Einstein-Rosen bridges, the in ER=EPR, are hypothetical tunnels through spacetime that could connect distant regions or even different universes. Quantum entanglement, on the other hand, is the phenomenon where two particles become linked. no matter how far apart they are, so that the state of one instantly affects the state of the other. The AR equals EPR conjecture suggests that entanglement might create a kind of shortcut through spacetime, essentially a wormhole. In other words, the entangled particles aren't just connected by some invisible force, they're linked by a hidden bridge in the fabric of reality. Now let's bring black holes into the picture. According to this theory, the singularity at the center of a black hole, a point of infinite density, might not be the end of the road. Instead, it could be the entrance to a wormhole, a tunnel leading to another region of spacetime or even another universe entirely. It's a breathtaking idea, black holes as cosmic doorways connecting our universe to a vast multiverse beyond. But how does this fit with what we know about black holes? One of the key insights comes from the work of Juan Maldacena, who proposed that the interior of a black hole might be described by a holographic principle, a framework where all the information about what's inside a black hole is encoded on its surface or event horizon. This idea, known as the holographic principle, suggests that the three-dimensional space we experience might be a projection of information stored on a two-dimensional surface. If true, it could mean that black holes aren't just singularities but complex structures with hidden connections to other regions of spacetime. Of course, this is all theoretical for now. We don't yet have the technology to peer inside a black hole or test these ideas directly. But the math behind ER equals EPR and the holographic principle is compelling, offering a tantalizing glimpse into how black holes might fit into a larger cosmic tapestry. And if black holes really are gateways to other universes, it would mean that the multiverse isn't just out there, it might be closer than we think, lurking in the shadows of these enigmatic objects. As we explore these ideas, a natural question arises. If black holes can connect different regions of spacetime, could they also be the key to understanding a holographic multiverse? This concept takes the holographic principle to the next level, suggesting that our entire universe, and perhaps the multiverse itself, might be a projection of information encoded on a lower dimensional surface. It's a radical idea, but one that could reshape our understanding of reality. And it's where our journey takes us next as we dive into the fascinating world of holography and what it might reveal about the cosmos. What if everything we see, touch, and experience is just a projection, a cosmic illusion created by information encoded on a distant, two-dimensional surface? This is the essence of the holographic principle, one of the most mind-bending ideas in modern physics. Imagine watching a movie on a flat screen. The image appears three-dimensional, but it's actually just a clever arrangement of pixels on a flat surface. Now take that concept and apply it to the entire universe. According to the holographic principle, our three-dimensional reality, complete with stars, planets, and galaxies, might be a projection of information stored on a two-dimensional boundary, like the surface of a black hole or the edge of the cosmos. It's a strange and beautiful idea, and it might just hold the key to understanding the multiverse. The roots of this principle trace back to the work of physicists Gerard T. Hooft and Leonard Susskind, who first proposed it in the 1990s. They were trying to solve a puzzle. How does a black hole preserve information about the objects it swallows? According to quantum mechanics, information can never be destroyed, but black holes seem to defy this rule. To resolve the paradox, T. Hooft and Susskind suggested that all the information about what falls into a black hole isn't lost, it's encoded on the black hole's event horizon, the boundary beyond which nothing can escape. This idea, later expanded by Susskind and others, gave birth to the holographic principle, which proposes that all the information in a volume of space can be represented as a kind of hologram on its boundary. But what does this have to do with the multiverse? If the holographic principle applies to black holes, could it also apply to the universe as a whole, or even to a collection of universes? Some physicists think so. They've proposed that our universe might be a holographic projection from a higher dimensional reality, and that other universes could exist as projections from their own cosmic boundaries. In this view, the multiverse isn't just a collection of separate worlds, it's a vast, interconnected network of holograms, each one encoding a unique reality. It's a bit like a library where every book represents a different universe, and the pages are written on a two-dimensional surface we can't see. This idea has profound implications for how we understand reality. If the universe is a hologram, then space and time might not be fundamental. They could emerge from something deeper, like the pixels on a screen. It also raises questions about the nature of existence itself. Are we and everything around us just patterns of information? And if so, what or who is projecting them? These are questions that blur the line between physics and philosophy, and they're still far from being answered. The holographic principle also offers a new way to think about the multiverse. If all universes are encoded on cosmic boundaries, then the multiverse might not be a chaotic jumble of worlds but a carefully structured system, where each universe is a unique projection from a higher dimensional reality. This idea ties together some of the most cutting-edge theories in physics, from string theory to quantum gravity, and it suggests that the multiverse could be far more interconnected and far stranger than we ever imagined. But the holographic principle isn't just about physics. It challenges us to rethink our place in the cosmos and the nature of reality itself. If the universe is a hologram, then what does that mean for consciousness? Could our awareness be part of the projection, or is it something deeper? This is where the story takes a fascinating turn, as we explore the role of consciousness in multiverse theories and how our minds might shape the reality we experience. Ready to dive into the mind-bending intersection of physics and perception? Let's go. What if the multiverse isn't just a collection of physical realities, but something shaped or even created by the very act of observing it? This might sound like the plot of a sci-fi movie, but it's a question that some scientists and philosophers are seriously exploring. At the heart of this idea is the concept of consciousness, not just as a byproduct of the brain, but as something fundamental to the fabric of reality itself. Could our awareness play a role in shaping the multiverse, or even in determining which universe we experience? Let's dive into some of the most intriguing theories that connect consciousness to the cosmos. One of the boldest ideas in this space is biocentrism, a theory proposed by scientist Robert Lanza. At its core, biocentrism suggests that consciousness isn't just a feature of the universe, it's the foundation of it. In Lanza's view, the universe only exists because there are conscious beings to observe it. Without observers, reality as we know it would collapse into a haze of probabilities. This idea builds on the principles of quantum mechanics, where particles exist in multiple states until they're observed. Biocentrism takes this a step further, proposing that the act of observation doesn't just affect reality, it creates it. In a multiverse context, this could mean that every conscious being is constantly selecting which universe they experience, based on their observations and choices. It's a radical reimagining of reality, one that places consciousness at the center of the cosmic story. Then there's panpsychism, a theory that takes a slightly different approach. Unlike biocentrism, which puts consciousness at the top of the hierarchy, panpsychism suggests that consciousness is a fundamental property of the universe like mass or charge. According to this view, even the smallest particles have a tiny spark of awareness, and complex consciousness emerges when these sparks come together in systems like brains. Thinkers like philosopher David Chalmers have argued that panpsychism could help solve the hard problem of consciousness, the question of how subjective experience arises from physical processes. If consciousness is woven into the fabric of reality, then the multiverse might not just be a collection of physical worlds, but a tapestry of experiences, each one unique and alive in its own way. Of course, these ideas are speculative, and they've sparked plenty of debate. Critics argue that theories like biocentrism and panpsychism are difficult to test, relying more on philosophical reasoning than hard evidence. But for their proponents, these ideas offer a way to bridge the gap between the physical and the experiential, between the universe as we describe it with equations and the universe as we live it. If consciousness is fundamental, then the multiverse might not just be a place of infinite possibilities. It could be a place of infinite experiences, each one shaped by the minds that inhabit it. As we explore these ideas, it's worth asking, what does this mean for us? If our consciousness plays a role in shaping reality, does that give us a kind of cosmic responsibility? And how might the existence of other conscious beings in other universes change the way we see ourselves and our place in the cosmos? These are questions that take us beyond physics and into the realm of ethics, a natural next step in our journey through the multiverse. What happens when we start thinking not just about what the multiverse is, but what it means for how we should live? That's where we're headed next. As we journey deeper into the multiverse, we arrive at a crossroads where science meets morality. If there are infinite versions of us, each making different choices in parallel realities, what does that mean for our sense of responsibility? Are we accountable only for the actions we take in this universe, or do the choices of our alternate selves also weigh on our conscience? These are the kinds of questions that challenge our ethical frameworks, forcing us to rethink what it means to live a good life. Consider this: in one universe, you might be a philanthropist dedicating your life to helping others. In another, you could be making selfish choices that harm those around you. If both versions of you exist, does that dilute the moral weight of your actions here and now? Some philosophers argue that the existence of alternate selves doesn't absolve us of responsibility. After all, the version of you in this universe is still making its own choices. Others suggest that the multiverse complicates traditional ideas of morality, introducing a kind of cosmic relativism where every possible action is happening somewhere. It's a debate that pushes us to consider whether ethics are universal or contingent on the specific reality we inhabit. But the multiverse doesn't just challenge our ideas of responsibility, it also raises questions about identity. If every decision creates a new universe, are we still the same self across all these realities? And if not, what binds us to the choices we make in this one? This line of thinking can lead to existential anxiety as we grapple with the idea that our lives are just one thread in an infinite tapestry. At the same time, it can also be liberating. If every possible version of you exists, then the pressure to make the perfect choice might feel less overwhelming. After all, somewhere out there, another version of you has already taken the path you didn't. These ethical and existential dilemmas aren't just abstract thought experiments, they have real-world implications. For instance, if we accept that our actions ripple across the multiverse, does that change how we approach global challenges like climate change or inequality? Could the multiverse inspire us to act with greater empathy, knowing that our choices might echo across countless realities? Or could it lead to a kind of moral paralysis, where the sheer scale of infinite possibilities makes it hard to feel that anything truly matters? These are questions without easy answers, but they remind us that the multiverse isn't just a scientific idea, it's a lens through which we can examine our values and beliefs. As we wrestle with these profound questions, it's worth noting that the multiverse doesn't exist in a vacuum. It's a concept that resonates deeply with human culture, appearing not just in science but in religion and spirituality as well. From ancient myths to modern faiths, the idea of multiple worlds has long been a source of inspiration and contemplation. And as we'll see next, exploring the multiverse through these lenses can shed new light on both the cosmos and ourselves. So let's turn our attention to how the multiverse has shaped and been shaped by the spiritual and religious imagination. The multiverse isn't just a modern scientific idea, it's a concept that has deep roots in human spirituality and religion. Across cultures and centuries, the idea of multiple worlds or realities has appeared in myths, scriptures, and philosophical traditions, often serving as a way to explore profound questions about existence, divinity, and the nature of reality. Take Hindu cosmology, for example. In Hinduism, the universe is often described as one of countless lokas or realms, each with its own distinct characteristics and inhabitants. These realms aren't just physical spaces but also states of consciousness, reflecting the belief that reality is layered and interconnected. The idea of a multiverse isn't just an abstraction here, it's woven into the very fabric of spiritual practice, reminding us that our world is just one thread in a vast cosmic tapestry. Buddhist philosophy offers another intriguing parallel. In Buddhism, the concept of samsara, the endless cycle of birth, death, and rebirth, can be seen as a kind of multiverse in itself. Each life, each existence is like its own universe, shaped by karma and the choices made within it. But beyond samsara lies nirvana, a state beyond all dualities and distinctions. In this framework, the multiverse isn't just a collection of physical worlds, but a metaphor for the infinite possibilities of existence and liberation. It's a reminder that reality, as we experience it, is fluid and ever-changing, shaped by both our actions and our perceptions. Even in Western traditions, there are echoes of the multiverse. Some interpretations of Christian theology, for instance, suggest that God's creation might extend beyond our own universe. Theologians like Thomas Aquinas speculated about the existence of multiple worlds, not as a challenge to divine power but as an expression of its boundless creativity. And in modern spirituality, the multiverse has taken on new life, often framed as a way to explore personal growth and the idea of alternate paths. For many, the multiverse is less about physics and more about possibility, a way to imagine different versions of ourselves and the lives we might have led. But while these spiritual and religious perspectives offer fascinating parallels, they also raise questions. If the multiverse is real, does it challenge traditional beliefs about creation, destiny, or the afterlife? Or does it expand our understanding of these concepts, offering new ways to think about the divine and the infinite? These are questions that bridge the gap between science and spirituality, inviting us to consider how the multiverse might resonate with or reshape our deepest beliefs about the cosmos and our place within it. As we explore these intersections, it's worth noting that the multiverse isn't just a backdrop for philosophical musings. It's also a lens through which we can examine modern challenges like the rise of artificial intelligence. If the multiverse is a place of infinite possibilities, what role might AI play in shaping or even creating those possibilities? That's where our journey takes us next as we dive into the fascinating connections between the multiverse and the future of technology. As we explore the multiverse, it's impossible to ignore the role of artificial intelligence, a technology that's reshaping not just our world, but potentially our understanding of reality itself. AI is already revolutionizing fields like medicine, finance, and even art, but could it also help us unlock the secrets of the multiverse? Some scientists think so. In fact, advanced AI systems might one day become our most powerful tools for exploring, or even simulating the infinite possibilities of parallel universes. But how? One of the most exciting possibilities is using AI to analyze the vast amounts of data generated by cosmological observations. Think about it: the cosmic microwave background, the distribution of galaxies, the behavior of particles at quantum scales. These are all areas where AI could spot patterns or anomalies that human researchers might miss. For example, AI algorithms could sift through the subtle irregularities in the CMB, searching for signs of collisions between our universe and others. Or they could model complex quantum systems, simulating how particles behave across countless branching realities. It's like giving scientists a supercharged microscope, one that can peer into the hidden corners of the cosmos. But AI's potential goes beyond data analysis. some researchers, like MIT physicist Max Tegmark, have suggested that AI could help us test multiverse theories by creating simulations of alternate universes. Imagine a future where AI systems are powerful enough to model entire universes, each with its own set of physical laws and constants. By running these simulations, we might be able to explore how different universes evolve and whether life could exist under conditions vastly different from our own. It's a bit like running a cosmic experiment where AI becomes both the scientist and the lab. Of course, this raises some fascinating and slightly unsettling questions. If AI can simulate entire universes, could it one day discover evidence of the multiverse itself? And if it does, how would we interpret those findings? After all, AI operates on logic and data, not intuition or philosophy. Could a machine truly understand the implications of infinite realities? Or would it simply present us with answers that challenge everything we thought we knew? These are questions that blur the line between science and speculation, but they remind us that AI isn't just a tool, it's a partner in our quest to understand the cosmos. As we look to the future, it's clear that AI will play an increasingly important role in our exploration of the multiverse, but it's not the only frontier we're pushing. Another concept that's deeply intertwined with the multiverse is time travel, a topic that's as mind-bending as it is tantalizing. What if the multiverse isn't just about parallel realities, but also about alternate timelines? And what would it mean to journey through them? That's where our story takes its next fascinating turn. Time travel has long been a staple of science fiction, but what if it's not just about moving through our own timeline? What if traveling through time actually involves stepping into other universes? This idea might sound like something out of a blockbuster movie, but it's a concept that some physicists take seriously, and it's deeply tied to the multiverse. At the heart of this idea is the notion that time travel doesn't just shuffle events within a single timeline. It could create branching paths leading to entirely new realities. Think of it like this: every time you travel back in time, you're not just altering history, you're creating a new history, one that unfolds in a parallel universe. It's a mind-bending twist on the classic time travel narrative, and it opens up a whole new way to think about the multiverse. One of the key figures in this field is physicist Kip Thorne, whose work on wormholes and general relativity has reshaped our understanding of space-time. Thorne proposed that wormholes, hypothetical tunnels through space-time, could serve as gateways for time travel. But here's the catch: traversing a wormhole wouldn't just take you to a different point in time, it might also transport you to a different universe. This is because wormholes could connect not just distant regions of space, but different branches of reality. Imagine stepping through a wormhole and finding yourself in a world where the dinosaurs never went extinct, or where humanity never discovered electricity. Each journey through time could become a journey into a new universe with its own unique history and future. But how does this connect to the multiverse? According to some interpretations of quantum mechanics, every decision or event creates a branching point, leading to a new universe. In this framework, time travel wouldn't just be about changing the past, it would be about exploring the infinite possibilities of the multiverse. For example, if you traveled back in time to prevent a major historical event, you wouldn't erase that event from existence. Instead, you'd create a new timeline where the event never happened, while the original timeline continues to exist in its own universe. It's a bit like flipping through the pages of a cosmic choose-your-own-adventure book, where every choice leads to a new story. Of course, this raises some fascinating and slightly unsettling questions. If time travel creates new universes, does that mean every version of history exists somewhere? And if so, does that make our actions less consequential, since there's always another universe where things turned out differently? These are questions that blur the line between physics and philosophy, and they are far from being settled. But they remind us that the multiverse isn't just a collection of worlds, It's a dynamic, ever-changing landscape shaped by the choices we make and the paths we take. As we explore these ideas, it's worth noting that time travel and the multiverse aren't just theoretical curiosities. They're deeply intertwined with some of the most cutting-edge research in physics, from quantum mechanics to string theory. And as we'll see next, these connections lead us to an even more radical idea, the quantum multiverse. This concept takes the idea of parallel universes to a whole new level, suggesting that the multiverse isn't just a product of branching timelines. It's woven into the very fabric of reality at the quantum level. Ready to dive deeper, let's explore how the quantum world might hold the key to understanding the multiverse. At the heart of quantum mechanics lies one of the most baffling and fascinating ideas in all of science: superposition. This principle tells us that particles can exist in multiple states at once, like being in two places simultaneously or spinning in opposite directions until they're observed. But what if this strange behavior isn't just confined to the tiny world of atoms? What if it's a window into a much larger reality, one where every possible outcome of every event is realized in its own universe? This is the essence of the quantum multiverse, a concept that takes the weirdness of quantum mechanics and scales it up to cosmic proportions. Think of it like this: when a particle is in superposition, it's not just undecided about its state, it's exploring all possible states at once. The moment we observe it, the superposition collapses and we see just one outcome. But according to the quantum multiverse interpretation, the other outcomes don't disappear. Instead, they branch off into their own realities, creating new universes where each possibility plays out. It's as if the universe is constantly splitting into countless versions of itself, each one reflecting a different path that could have been taken. This idea, championed by physicists like David Deutsch, suggests that the quantum world is teeming with parallel realities, each one as real as our own. But superposition isn't the only quantum phenomenon that hints at a multiverse. Quantum entanglement, the eerie connection between particles that can't be explained by classical physics, also plays a role. When two particles become entangled, their properties are linked no matter how far apart they are. Change one, and the other changes instantly, faster than the speed of light. This spooky action at a distance, as Einstein called it, seems to defy the limits of space and time. But what if it's not defying those limits? What if it's revealing a deeper connection between different universes? Some theories suggest that entangled particles might be linked across parallel realities, acting as bridges between worlds that are otherwise inaccessible. These ideas aren't just mind-bending thought experiments, they have real implications for how we understand reality. If the quantum multiverse is real, then every observation we make, every measurement we take, isn't just revealing the state of the universe, it's selecting one universe out of an infinite array of possibilities. This raises profound questions about the role of the observer. Are we the creators of our reality, collapsing superpositions into a single outcome with every act of observation? Or are we just one thread in a vast, interconnected web of universes, each one shaped by the choices of countless observers? David Deutsch, one of the pioneers of the quantum multiverse idea, has argued that this framework isn't just a philosophical curiosity, it's a practical tool for understanding the universe. By embracing the idea of parallel realities, we can make sense of phenomena that would otherwise seem inexplicable. For example, the infamous double-slit experiment, where particles behave like waves when unobserved and like particles when observed, becomes much clearer when viewed through the lens of the multiverse. Instead of a single particle choosing a path, we have countless particles exploring all possible paths across countless universes. It's a perspective that turns confusion into clarity, offering a new way to navigate the quantum world. But the implications of the quantum multiverse go even further. If every possible outcome exists somewhere, then the universe is far richer and more complex than we ever imagined. Every choice, every event creates a branching point leading to an ever-expanding tree of realities. This challenges our traditional notions of causality and determinism, suggesting that the future isn't just a single path but a sprawling network of possibilities. And it raises questions about free will. If every decision spawns a new universe, are we truly making choices, or are we simply following the branching paths of an infinite multiverse? As we delve deeper into the quantum multiverse, one thing becomes clear: the boundaries between science and philosophy are blurrier than ever. This isn't just about particles and probabilities, it's about the very nature of existence. And while the quantum multiverse might seem like a radical idea, it's one that's firmly grounded in the mathematics of quantum mechanics. But how does this quantum framework fit into the larger picture of the cosmos? To answer that, we need to zoom way out, and explore how the multiverse fits into the grand tapestry of cosmology. That's where our journey takes us next. As we zoom out from the quantum world and into the vast expanse of the cosmos, the multiverse takes on an even grander scale. Here, it's not just about particles or timelines, it's about the very fabric of reality itself, woven into the history of the universe. To understand how the multiverse fits into cosmology, we need to go back to the beginning, the Big Bang. This explosive event, roughly 13.8 billion years ago, marks the birth of our universe. But what if it wasn't the only birth? What if the Big Bang was just one of countless cosmic beginnings, each giving rise to its own unique universe? This is where the multiverse meets cosmology, and it's a story that begins with a concept called cosmic inflation. Cosmic inflation is the idea that, in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching from a tiny speck to an incomprehensibly large size. This rapid growth explains why the universe appears so uniform and why distant regions of space look so similar. But inflation doesn't stop there. According to physicists like Andre Lind, inflation might not have been a one-time event, it could still be happening. In this view, different regions of space could stop inflating at different times, creating bubble universes that float within a much larger multiverse. Each bubble would have its own set of physical laws and constants, making our universe just one among an infinite number of possibilities. This idea, known as the inflationary multiverse, suggests that the cosmos isn't a single, isolated entity but part of a vast cosmic landscape. Picture a boiling pot of water where bubbles form and pop on the surface. In this analogy, each bubble is a universe and the pot itself is the multiverse. Some bubbles might have stronger gravity, others might have extra dimensions, and some might be entirely unrecognizable to us. Our universe is just one lucky bubble with the right conditions for stars, planets, and life to emerge. It's a humbling thought, but also an inspiring one, as it hints at the sheer diversity of existence. Cosmologists like Lind have spent decades refining this idea, using mathematical models and observational data to explore how inflation could give rise to a multiverse. One of the key pieces of evidence comes from the cosmic microwave background, or CMB, the faint glow of light left over from the Big Bang. Tiny fluctuations in the CMB align remarkably well with predictions from inflationary theory, suggesting that our universe did indeed undergo a rapid expansion in its infancy. While we can't directly observe other bubble universes, the success of inflationary cosmology lends credibility to the idea that our universe might be part of a much larger cosmic tapestry. But the multiverse isn't just a theoretical curiosity, it's a natural extension of some of the most well-supported ideas in cosmology. It offers a way to explain why our universe seems so finely tuned for life, suggesting that in the vastness of the multiverse, every possible combination of physical laws exists somewhere. It also challenges us to think bigger, to imagine a cosmos that's far more complex and interconnected than we ever realized. And as we'll see next, this interconnectedness isn't just a feature of cosmology, It's also a key theme in particle physics, where the multiverse takes on a whole new dimension. Let's dive in. Now, let's zoom in from the cosmic scale to the microscopic realm, where the smallest building blocks of reality might hold the key to unlocking the multiverse. Particle physics, the study of the fundamental particles and forces that make up the universe, has long been a cornerstone of our understanding of reality. But could it also offer clues about the existence of other universes? Surprisingly, the answer might lie in something as seemingly simple as the Higgs boson, the particle that gives mass to all others. The Standard Model of particle physics, our most comprehensive framework for understanding the subatomic world, has been remarkably successful in explaining how particles interact. Yet it leaves some big questions unanswered, like why the Higgs boson has the mass it does. This mass is crucial because it determines the strength of the forces that shape our universe. If the Higgs were even slightly heavier or lighter, the cosmos as we know it might not exist. This fine-tuning has led some physicists to wonder, could the Higgs mass be just one of many possible values, each realized in a different universe? In this view, our universe is one where the Higgs mass happens to be just right for life to emerge, while countless others might have values that render them barren. Physicists like Lisa Randall have explored how the Higgs boson and other particles could fit into a multiverse framework. Randall's work on extra dimensions, for example, suggests that particles like the Higgs might interact with hidden dimensions we can't see, potentially creating branes or membranes that act as separate universes. These branes could exist alongside ours, each with its own set of particles and forces. It's a bit like living in an apartment building where each floor is a different universe, but we can't see or interact with the neighbors above or below us. This idea not only ties particle physics to the multiverse, but also raises the possibility that collisions between branes could trigger events like the Big Bang, giving rise to new universes. But the Standard Model isn't without its challenges. For one, it doesn't include gravity, which remains one of the great unsolved puzzles in physics. This gap has led scientists to look beyond the Standard Model, exploring theories like supersymmetry and string theory, which predict the existence of particles we haven't yet detected. These theories also suggest that the multiverse might be a natural consequence of the underlying mathematics. For example, if supersymmetry is correct, it could mean that every particle we know has a heavier superpartner in another universe. These superpartners might interact in ways that shape the laws of physics in their respective worlds, creating a patchwork of universes with different rules. As we piece together these ideas, it's clear that particle physics isn't just about understanding our universe, it's about exploring the possibilities of countless others. The Higgs boson, extra dimensions, and the search for new particles are all part of a larger quest to uncover the hidden structure of reality. And while the multiverse remains a speculative idea, the work of physicists like Lisa Randall reminds us that the answers might be closer than we think. But what if the multiverse isn't just a collection of physical worlds? What if it's also a mathematical landscape where the laws of physics are just one expression of a deeper, abstract reality? That's where our journey takes us next, as we dive into the concept of a mathematical multiverse, a place where numbers, equations, and geometry might hold the key to understanding everything. Ready to explore? Let's go. What if the universe isn't just governed by mathematics? What if it is mathematics? This is the bold idea at the heart of the mathematical multiverse, a concept championed by physicist Max Tegmark. According to Tegmark, reality isn't just described by math, it's made of it. Every possible mathematical structure, from the simplest equations to the most complex geometries, exists as a physical reality somewhere in the multiverse. In this view, our universe is just one mathematical structure among an infinite array of others, each one as real as the numbers on this page. It's a radical reimagining of reality, one that blurs the line between the abstract and the tangible. To understand this idea, let's take a step back. Mathematics has long been the language of science, a tool we use to describe the behavior of particles, the motion of planets, and the expansion of the cosmos. But Tegmark takes this a step further, arguing that math isn't just a tool, it's the foundation of existence itself. Think of it like this: if the universe is a book, then mathematics isn't just the language it's written in, it's the paper, the ink, and the very act of writing. In Tegmark's framework, every equation, every geometric shape, and every logical structure corresponds to a real, physical universe, a universe where 2 + 2 = 5. It exists, a universe shaped like a 12-dimensional hypercube. It exists too. The mathematical multiverse is a place of infinite possibilities where every structure that can be imagined, or even those that can't, is realized somewhere. This idea isn't just a flight of fancy. It's grounded in the work of mathematicians and physicists who have long grappled with the relationship between math and reality. For example, physicist Eugene Wigner famously called the effectiveness of mathematics in describing the physical world unreasonable. Why should abstract numbers and equations so perfectly match the behavior of the universe? Tegmark's answer is simple: because the universe is math. Others, like mathematician Roger Penrose, have explored how mathematical structures like the Mandelbrot set, a fractal pattern that repeats infinitely at every scale, seem to mirror the complexity and beauty of the natural world. Could these patterns be more than just models? Could they be glimpses into the true nature of reality? But the mathematical multiverse isn't just about abstract theory. It has profound implications for how we understand existence. If every mathematical structure is a real universe, then the laws of physics we observe in our world aren't fundamental truths, they're just the rules of this particular mathematical game. In another universe, the rules might be entirely different, leading to realities that are unrecognizable to us. This challenges our traditional notions of what's possible, suggesting that the cosmos is far stranger and more diverse than we ever imagined. It also raises questions about the nature of consciousness and perception. If the universe is fundamentally mathematical, does that mean our minds are mathematical too? Are we, in some sense, living equations? These are questions that bridge the gap between science and philosophy, and they're far from being answered. Of course, not everyone is convinced. Critics argue that Tegmark's idea is untestable after all. How could we ever prove the existence of universes based on abstract equations? Others worry that it risks conflating the map with the territory, treating mathematical descriptions as if they were the things themselves. But for its proponents, the mathematical multiverse offers a way to unify physics and mathematics, bringing us closer to a theory of everything that explains not just our universe but all possible universes. It's a vision of reality that's as elegant as it is expansive, and it challenges us to think bigger than ever before. As we explore the mathematical multiverse, it's worth noting that this idea isn't entirely separate from the other multiverse theories we've discussed. In fact, it ties into one of the most ambitious frameworks in modern physics, string theory. String theory, with its extra dimensions and vibrating strings, is deeply mathematical, and some physicists have suggested that it could provide a bridge between the mathematical multiverse and the physical cosmos. But how does string theory fit into the larger multiverse puzzle? That's where our journey takes us next, as we dive into the intricate world of strings, brains, and the hidden dimensions that might hold the key to understanding everything. String theory has long been one of the most ambitious and elegant frameworks in modern physics, aiming to unify all the fundamental forces of nature under a single theoretical umbrella. But beyond its promise as a theory of everything, string theory also offers a fascinating lens through which to view the multiverse. At its core, string theory suggests that the universe isn't made of point-like particles, as we've traditionally thought, but of tiny, vibrating strings. These strings oscillate at different frequencies, giving rise to everything from quarks to photons. Yet, for the math to work, string theory requires something extraordinary: extra dimensions. Not just one or two, but 10 dimensions of space and one of time. These additional dimensions, though hidden from our everyday experience, could hold the key to understanding not just our universe, but a vast multiverse of others. One of the most striking implications of string theory is the concept of the string landscape. This idea, developed by physicists like Raphael Bousso and Leonard Susskind, suggests that the extra dimensions predicted by string theory can take on an almost infinite variety of shapes and configurations, each corresponding to a different set of physical laws. Imagine a vast cosmic terrain where every valley, hill, and plateau represents a unique universe with its own constants, forces, and particles. Some of these universes might have stronger gravity, others weaker nuclear forces, and some might even have entirely different dimensions of space. Our universe, with its finely tuned laws that allow for stars, planets, and life, is just one point in this sprawling landscape. This concept has profound implications. If the string landscape is real, it means that the multiverse isn't just a collection of random universes, it's a structured array of possibilities, each one governed by its own unique rules. Physicists like Edward Witten, a leading figure in string theory, have explored how these different configurations might arise naturally from the mathematics of the theory. Witten's work on M-theory, an extension of string theory, suggests that the extra dimensions could form intricate shapes known as Calabi-Yau manifolds. These geometric structures are so complex that they've been described as the DNA of the universe, encoding the fundamental properties of particles and forces. But they also hint at something even more profound: the possibility of entire universes existing as membranes or brains floating in higher dimensional space. In this view, our universe might be one such brain, drifting alongside countless others in a higher dimensional multiverse. The string landscape isn't just a theoretical curiosity, it offers a potential explanation for one of the most puzzling aspects of our universe: its fine-tuning. Why do the constants of nature, like the strength of gravity or the mass of the electron, have the precise values they do? The string landscape suggests that in the vastness of the multiverse, every possible combination of these constants exists somewhere. Our universe, with its life-friendly parameters, is just one lucky configuration in an infinite array of possibilities. It's a bit like finding a needle in a cosmic haystack, but on a scale that's almost impossible to comprehend. However, the string landscape isn't without its challenges. One of the biggest is the sheer complexity of the mathematics involved. Calabi-Yau manifolds, for example, are so intricate that even the most powerful supercomputers struggle to fully map their properties. And while the theory predicts an almost infinite number of possible universes, we currently have no way to test which, if any, of these configurations correspond to reality. Critics argue that this makes the string landscape untestable, at least with our current technology. But for its proponents, the elegance and explanatory power of the theory make it too compelling to ignore. As we explore these ideas, it's worth noting that string theory isn't just about particles and dimensions. It's also deeply connected to the concept of quantum gravity. This is the idea that gravity, the force that shapes the cosmos on the largest scales, can be unified with quantum mechanics, the framework that governs the smallest particles. String theory suggests that the extra dimensions it predicts might hold the key to this unification, offering a way to reconcile the two great pillars of modern physics. And if that's true, it could open the door to understanding not just our universe, but the multiverse itself. This brings us to the next chapter in our journey: the role of quantum gravity in shaping the multiverse. How does gravity, the force that binds galaxies and bends space-time, fit into the picture of a multiverse teeming with parallel realities? And could a deeper understanding of quantum gravity help us unlock the secrets of the cosmos? Let's dive in. Quantum gravity is one of the most elusive and tantalizing frontiers in physics. a field where the colossal force that shapes galaxies meets the bizarre, probabilistic world of quantum mechanics. At its heart lies a question that has puzzled scientists for decades. How do we reconcile the smooth, continuous fabric of spacetime, as described by Einstein's general relativity, with the discrete, quantized nature of the subatomic world? This isn't just an academic puzzle, it's a key to unlocking the multiverse. If spacetime itself is quantized, broken into tiny, indivisible units, then the very structure of reality might be far stranger than we ever imagined. One of the leading theories in this space is loop quantum gravity, developed by physicists like Carlo Rovelli and Abhay Ashtekar. Unlike string theory, which adds extra dimensions to the universe, loop quantum gravity takes a different approach. It suggests that spacetime isn't a smooth continuum but a network of tiny loops woven together like a cosmic tapestry. These loops are the fundamental building blocks of reality, and they create a kind of fabric that can stretch, twist, and bend. In this framework, the Big Bang might not have been the beginning of everything. It could have been a transition from a previous state of the universe, a cosmic bounce rather than a singular explosion. This idea has profound implications for the multiverse, as it opens the door to the possibility of multiple universes existing in a larger quantum spacetime framework. Imagine spacetime as a quilt stitched together from countless loops. Each stitch represents a quantum of spacetime, and the way these stitches connect determines the structure of the universe. But here's where it gets even more fascinating. In loop quantum gravity, the fabric of spacetime isn't static. It's dynamic, constantly evolving and interacting. This means that the boundaries between universes might not be fixed. Instead, they could shift and change, creating pathways for universes to interact or even merge. It's a vision of the multiverse that's not just about separate, isolated worlds, but about a deeply interconnected cosmic network. Carlo Rovelli, one of the pioneers of loop quantum gravity, has described this idea as a relational view of reality. In this framework, the properties of spacetime, and by extension, the multiverse, are defined by the relationships between its components, not by some fixed external structure. It's a bit like how the meaning of a word depends on its context in a sentence. In the same way, the nature of spacetime depends on how its quantum loops are connected. This relational approach challenges our traditional notions of space and time, suggesting that the multiverse might be a living, breathing entity, constantly reshaping itself in ways we're only beginning to understand. But loop quantum gravity isn't the only theory exploring the quantum structure of spacetime. Other approaches, like causal dynamical triangulations and spin foam models, also suggest that spacetime might be quantized. These theories use different mathematical tools to describe how spacetime emerges from the interactions of its smallest components, but they share a common theme. The multiverse isn't just a collection of physical worlds, it's a manifestation of the underlying quantum geometry of reality. As we explore these ideas, it's worth asking, what does a quantized spacetime mean for the multiverse? If spacetime itself is made of discrete units, then the boundaries between universes might not be as rigid as we think. Instead, they could be fluid, with universes forming, interacting, and dissolving within a larger quantum framework. This opens up the possibility of a multiverse that's not just a static array of worlds but a dynamic, evolving system, shaped by the fundamental laws of quantum gravity. But the story doesn't end here. As we've seen, quantum gravity offers a new way to think about the multiverse, but it's just one piece of the puzzle. To truly understand how the multiverse fits into the grand tapestry of the cosmos, we need to zoom out, way out, and explore the role of cosmology. How does the multiverse fit into the history and future of the universe? And what clues might the cosmos itself hold about the existence of other worlds? That's where our journey takes us next. The Big Bang has long been considered the cosmic starting gun, the moment when our universe burst into existence, setting the stage for everything we see today. But what if the Big Bang wasn't the beginning of everything? What if it was just one event in a much larger, more complex multiverse? This is where the idea of an inflationary multiverse comes into play, and it's a theory that could reshape how we think about the origins of our universe. At the heart of this idea is cosmic inflation, a period of rapid expansion that occurred just moments after the Big Bang. Proposed by physicist Alan Guth in the early 1980s, inflation explains why the universe appears so uniform on large scales and why it's filled with the seeds of galaxies and cosmic structures. But here's the twist: inflation might not have been a one-time event. Instead, it could be an ongoing process with different regions of space inflating at different times, creating bubble universes that float within a much larger multiverse. Think of it like a cosmic pot of boiling water, where each bubble represents a universe with its own unique properties. Our universe is just one of countless bubbles, each one born from its own inflationary event. This concept, further developed by physicists like Andre Linde, suggests that the Big Bang wasn't the ultimate beginning, it was just the start of our particular bubble. In other regions of the multiverse, inflation might still be happening, giving rise to new universes all the time. Some of these universes might have different physical constants, different numbers of dimensions, or even entirely different laws of physics. It's a staggering idea, but one that offers a potential explanation for why our universe seems so finely tuned for life. In the vastness of the multiverse, every possible combination of physical laws exists somewhere, and we just happen to be in the one where life can thrive. But how does this connect to what we can observe? The cosmic microwave background, or CMB, the faint glow of light left over from the Big Bang, holds subtle clues. Tiny fluctuations in the CMB align remarkably well with predictions from inflationary theory, suggesting that our universe did indeed undergo rapid expansion in its infancy. While we can't directly observe other bubble universes, the evidence for inflation lends credibility to the idea that our universe might be part of a much larger cosmic landscape. Critics, of course, raise valid questions. If these other universes are forever beyond our reach, how can we ever prove they exist? And if inflation creates an infinite number of universes, does that make the theory untestable? These are challenges that physicists continue to grapple with, but the inflationary multiverse remains one of the most compelling frameworks for understanding the cosmos and our place within it. As we piece together these ideas, it's clear that the Big Bang isn't just the story of our universe, it's a chapter in a much larger cosmic saga. And while the multiverse might seem like a speculative idea, it's deeply rooted in some of the most well-supported theories in physics. But there's another piece of the puzzle that could help us understand the multiverse even further: dark matter. This mysterious substance, which makes up most of the matter in the universe, might hold clues about the hidden structure of the multiverse itself. Ready to explore how dark matter fits into the picture? Let's dive in. Dark matter, an invisible, mysterious substance that makes up about 85% of the matter in the universe, has long been one of the greatest puzzles in modern physics. We can't see it, we can't touch it, but its gravitational pull shapes galaxies, bends light, and holds the cosmos together. Yet, for all its importance, we still don't know what dark matter actually is. Could it be more than just a cosmic placeholder? Could it hold clues about the multiverse itself? Some physicists think so, suggesting that dark matter might be a remnant of interactions between universes, a kind of cosmic fingerprint left behind by unseen dimensions or parallel realities. One of the most intriguing ideas comes from physicist Lisa Randall, who has explored how dark matter could be connected to extra dimensions predicted by string theory. Randall's work suggests that dark matter might not be confined to our universe alone. Instead, it could exist in a higher dimensional space, interacting with our universe only through gravity. Imagine a sheet of paper lying flat on a table. If you were a two-dimensional being living on that paper, you'd never see the three-dimensional world around you, but you might feel its effects. Similarly, dark matter could be leaking into our universe from another dimension, leaving traces of its presence in the form of gravitational effects we can't otherwise explain. But there's another possibility. Dark matter might not just exist alongside our universe, it could be a relic of interactions between universes. In some multiverse theories, universes are thought to exist as membranes or brains floating in higher dimensional space. These brains can sometimes collide or interact, creating ripples in spacetime that could leave behind particles like dark matter. Think of it like two soap bubbles gently bumping into each other. The point of contact could leave a mark, a kind of cosmic residue that lingers long after the interaction has ended. In this scenario, dark matter might be the result of ancient collisions between our universe and others, a hidden reminder of a multiverse we can't yet see. Of course, these ideas are speculative, and dark matter remains one of the most elusive subjects in physics. But the very fact that we're asking these questions shows how far our understanding has come. Dark matter isn't just a missing piece of the puzzle, it's a window into a deeper, more complex reality. And as we continue to search for answers, whether through particle colliders, telescopes, or simulations, we might find that dark matter holds the key to unlocking the secrets of the multiverse. But dark matter isn't the only cosmic mystery that could shed light on the multiverse. As we'll see next, another cutting-edge field, quantum computing, might offer a way to explore the multiverse in ways we never thought possible. What happens when the power of quantum mechanics is harnessed to simulate the infinite possibilities of parallel realities? The answers might be closer than we think. Quantum computing isn't just revolutionizing technology, it's opening up entirely new ways to explore the multiverse. At its core, a quantum computer operates on principles that sound like they're straight out of science fiction: superposition, entanglement, and the ability to process multiple possibilities simultaneously. These same principles are at the heart of multiverse theories, making quantum computers uniquely suited to simulating the infinite complexities of parallel realities. Imagine a machine that doesn't just calculate probabilities but actually embodies them, exploring every possible outcome of a quantum event in real time. That's the power of quantum computing, and it might just hold the key to unlocking the secrets of the multiverse. One of the pioneers in this field is Seth Lloyd, a quantum physicist at MIT. Lloyd has proposed that quantum computers could be used to simulate entire universes, complete with their own sets of physical laws and constants. In this framework, a quantum computer wouldn't just crunch numbers, it would create a virtual multiverse where every possible configuration of particles, forces, and dimensions could be explored. Think of it like running a cosmic video game where each level represents a different universe with its own unique rules. By tweaking the parameters of the simulation, researchers could test how different physical laws affect the evolution of galaxies, the formation of stars, or even the emergence of life. It's a mind-bending application of quantum computing, and one that could bring multiverse theories out of the realm of speculation and into the lab. But how does this actually work? Quantum computers use qubits, quantum bits that can exist in multiple states at once thanks to superposition. Unlike classical bits, which are either 0 or 1, qubits can be 0, 1, or both simultaneously. This allows quantum computers to process vast amounts of information in parallel, making them ideal for simulating the branching paths of the multiverse. For example, a quantum computer could model the many worlds interpretation of quantum mechanics, where every possible outcome of an event spawns a new universe. By simulating these branching realities, scientists could gain insights into how the multiverse might function, and whether it's a plausible explanation for the strange behavior of particles at the quantum level. Of course, this is still a work in progress. Current quantum computers are relatively small and prone to errors, limiting their ability to simulate complex systems. But as the technology advances, so too does the potential for exploring the multiverse. Researchers are already using quantum computers to model simpler quantum systems, like the behavior of molecules or the properties of materials. These early experiments are laying the groundwork for more ambitious simulations, where entire universes could be created and analyzed in the blink of an eye. It's a thrilling prospect and one that could transform our understanding of reality. As we look to the future, it's clear that quantum computing offers a powerful tool for exploring the multiverse. But the multiverse isn't just a playground for physicists and computer scientists. It's a concept that resonates across disciplines, from cosmology to biology. Speaking of biology, what happens when we bring the multiverse into the realm of life itself? How might the existence of parallel universes shape our understanding of evolution, genetics, and the origins of life? That's where our journey takes us next, as we explore the multiverse through the lens of biology. Ready to dive in? Let's go. What if life as we know it isn't the only way it can exist? What if, in another universe, the rules of biology are so different that life takes on forms we can't even imagine? This is where the multiverse collides with biology, opening up a whole new realm of possibilities. If the multiverse exists, it's not just a collection of alternate physical laws, it's a playground for alternate forms of life. From the building blocks of DNA to the very concept of survival, the multiverse challenges us to rethink what it means to be alive. Let's start with the basics. Life on Earth is carbon-based, relying on water, DNA, and a delicate balance of chemical reactions to thrive. But in another universe, the fundamental ingredients might be completely different. Imagine a world where silicon, not carbon, forms the backbone of life, or where ammonia replaces water as the solvent for biochemical reactions. Astrobiologists like Sarah Seeger have spent years exploring how life might arise in environments vastly different from Earth's, from methane-rich lakes on Titan to the icy oceans of Europa. These studies don't just prepare us for finding life elsewhere in our universe, they hint at the staggering diversity of life that could exist across the multiverse. In some universes, the laws of physics might allow for life forms that don't rely on chemistry at all. Picture a universe where electromagnetism is stronger, enabling energy-based beings to exist. Or one where gravity is weaker, allowing for gigantic, floating organisms that drift through the skies. These aren't just speculative ideas, they're grounded in the understanding that life adapts to its environment, no matter how extreme or unfamiliar. The multiverse suggests that the possibilities for life are as infinite as the universes themselves, each one shaped by its own unique set of physical laws. But the multiverse doesn't just change how we think about life, it also reshapes our understanding of evolution. On Earth, natural selection favors traits that enhance survival and reproduction, leading to the incredible diversity of species we see today. But in a multiverse, evolution might play out in ways we can't predict. In a universe with stronger radiation, for example, life might evolve with incredibly efficient DNA repair mechanisms. In another, where time flows differently, organisms might have lifespans that stretch across millennia or flash by in seconds. The multiverse forces us to consider that evolution isn't a one-size-fits-all process, it's a cosmic dance choreographed by the unique conditions of each universe. Sarah Seeger's work in astrobiology has been instrumental in pushing these boundaries. By studying exoplanets and the potential for life beyond Earth, she and others are uncovering the universal principles that might govern life across the multiverse. Whether it's identifying biosignatures in alien atmospheres or modeling how life might arise in extreme environments, their research is laying the groundwork for understanding how life could exist in universes with entirely different rules. It's a reminder that biology, like physics, is shaped by the conditions of the universe it inhabits. As we explore the intersection of biology and the multiverse, it's worth asking, what does this mean for our understanding of life? If life can exist in infinite forms across infinite universes, does that make our existence more or less special? These questions aren't just scientific, they're deeply philosophical. And as we'll see next, the multiverse doesn't just challenge our understanding of life and evolution, it forces us to rethink the very nature of science itself. What happens when the multiverse meets the philosophy of science? That's where our journey takes us next. The multiverse isn't just a scientific idea, it's a philosophical puzzle that challenges the very foundations of how we do science. Traditionally, science has been built on the principle of falsifiability, a concept championed by philosopher Karl Popper. For a theory to be scientific, Popper argued, it must be possible to prove it wrong. This means that a good scientific theory makes predictions that can be tested and potentially disproven through observation or experiment. But what happens when a theory like the multiverse comes along, proposing realities that are, by definition, beyond our ability to observe or interact with? Does it still count as science, or does it drift into the realm of philosophy? This question has sparked heated debates among scientists and philosophers alike. On one side of the debate are those who argue that the multiverse, while fascinating, falls outside the bounds of traditional scientific inquiry. Critics like physicist Paul Steinhardt have pointed out that if we can't observe or test other universes, the multiverse becomes untestable and therefore unscientific. It's a bit like saying, there's an explanation for everything but you can't see it. For these thinkers, the multiverse risks becoming a theory of anything, offering explanations for phenomena without providing a clear way to verify them. This lack of falsifiability, they argue, undermines the rigor and reliability of science, turning it into speculation rather than discovery. On the other side are those who believe the multiverse is a natural extension of well-supported scientific theories like inflation or quantum mechanics. They argue that even if we can't directly observe other universes, the multiverse framework makes predictions about our own universe that can be tested. For example, the cosmic microwave background might hold subtle imprints of collisions between our universe and others, as we discussed earlier. While these predictions are challenging to verify, they're not impossible, and as technology advances, so too might our ability to gather evidence. In this view, the multiverse is a bold but testable hypothesis, pushing the boundaries of what science can explore. Philosophers like Karl Popper might have been skeptical of the multiverse, but they also recognized that science evolves. New ideas often start as untestable speculations before becoming testable theories. Think of how the idea of atoms was once a philosophical concept, debated by ancient Greeks before becoming a cornerstone of modern physics. Could the multiverse follow a similar path? It's a question that forces us to rethink not just what we know, but how we know it. And as we grapple with these ideas, it's worth noting that the multiverse isn't just challenging science, it's reshaping it. This debate over the scientific status of the multiverse isn't just academic. It has real implications for how we approach the cosmos. If the multiverse is a valid scientific theory, it opens up entirely new avenues for exploration, allowing us to ask questions we might never have considered before. But if it's purely speculative, it risks diverting resources and attention away from more testable ideas. Striking the right balance between bold speculation and rigorous testing is one of the great challenges of modern science, and the multiverse sits right at the heart of it. As we wrestle with these questions, it's worth remembering that science isn't just about finding answers, it's about asking the right questions. And the multiverse, for all its controversy, is one of the most profound questions we've ever asked. But to truly understand its place in the cosmos, we need to zoom way out, and explore how the multiverse fits into the grand narrative of cosmology. What role does it play in the history and future of the universe? And what clues might the cosmos itself hold about the existence of other worlds? That's where our journey takes us next. The universe we live in seems almost too perfect to be an accident. The constants of nature, like the strength of gravity, the mass of an electron, or the energy of the Big Bang are so precisely calibrated that even the tiniest change would make life impossible. This fine-tuning has long puzzled scientists and philosophers alike. How did our universe end up with such ideal conditions? One compelling answer lies in the multiverse, a concept that suggests our universe is just one of many, each with its own unique set of rules. Imagine a vast cosmic lottery where every possible combination of physical constants exists somewhere. In some universes, gravity might be so strong that stars collapse into black holes almost instantly. In others, the forces that bind atoms together might be too weak to form stable matter. And then there's our universe, where the constants are just right for galaxies, stars, planets, and life to emerge. This idea, known as the Anthropic Principle, suggests that we observe a finely tuned universe not because it was designed, but simply because we're here to observe it. In a multiverse of infinite possibilities, it's statistically inevitable that at least one universe would have the conditions needed for life. Physicists like Martin Rees have explored this idea in depth, arguing that the multiverse offers a natural explanation for fine-tuning. Rees, a former astronomer royal and a leading figure in cosmology, has pointed out that the constants of nature don't seem to have any deeper explanation within our universe. They just are, but in a multiverse these constants become variables, each one set by the unique conditions of its universe. This shifts the question from why is our universe fine-tuned to why are we in the fine-tuned universe. It's a subtle but profound change in perspective, one that reframes fine-tuning as a selection effect rather than a mystery. Of course, not everyone is convinced. Critics argue that invoking a multiverse to explain fine-tuning is a bit like saying, anything can happen, so something must. It's a valid point, but proponents of the multiverse counter that it's the only framework we have that can naturally account for the precision of the constants. Without the multiverse, fine-tuning remains a puzzle with no clear solution. And while the multiverse might seem like a speculative idea, it's firmly grounded in well-supported theories like inflation and quantum mechanics. As we explore these ideas, it's worth noting that the multiverse doesn't just explain fine-tuning, it also raises fascinating questions about the nature of reality. If every possible configuration of physical laws exists somewhere, what does that mean for our understanding of the universe? Are we living in the best of all possible worlds, or just one of countless variations? These are questions that blur the line between science and philosophy, and they're far from being settled. But fine-tuning isn't the only cosmic puzzle the multiverse might help solve. As we'll see next, the multiverse also intersects with quantum field theory, a framework that describes how particles and forces interact at the most fundamental level. How does the multiverse fit into the strange and wonderful world of quantum fields? That's where our journey takes us next. Quantum field theory, a cornerstone of modern physics, might hold the key to understanding how the multiverse could exist. At its core, this theory describes how particles and forces interact, painting a picture of reality as a dynamic interplay of fields. These fields permeate all of space, vibrating at different frequencies to produce the particles we know, from electrons to photons. But what if these fields could do more than just create particles? What if they could give rise to entire universes? This is where quantum field theory intersects with the multiverse, offering a fascinating framework for how new universes might come into existence. One of the central ideas here is vacuum energy, a concept that sounds simple but is anything but. In quantum field theory, even empty space isn't truly empty. It's filled with a seething sea of energy, constantly fluctuating as particles pop in and out of existence. This energy, often referred to as the quantum vacuum, is a fundamental feature of the universe. But here's where it gets interesting. In some theories, this vacuum energy isn't uniform. Different regions of space can have different energy levels, and these variations could trigger the birth of new universes. Imagine a cosmic pressure cooker where pockets of high-energy vacuum boil and burst, creating bubbles of spacetime that expand into full-fledged universes. This process, known as quantum tunneling, suggests that the multiverse might be constantly bubbling with new realities, each one born from the quantum fluctuations of the vacuum. Physicists like Steven Weinberg have explored how vacuum energy could play a crucial role in shaping the multiverse. Weinberg, a Nobel laureate and one of the architects of the Standard Model of particle physics, has pointed out that the energy of the vacuum isn't just a theoretical curiosity, it has real consequences for the structure of the universe. In his work, Weinberg showed how the value of the vacuum energy in our universe is remarkably small, a fact that has puzzled scientists for decades. If it were much larger, galaxies and stars might never have formed. But in a multiverse, this fine-tuning makes sense. With infinite universes, each with its own vacuum energy, it's inevitable that some would have the low energy values needed for life to emerge. This idea ties quantum field theory directly to the multiverse, suggesting that the properties of our universe might be shaped by the larger cosmic landscape. But vacuum energy isn't the only way quantum field theory connects to the multiverse. Another intriguing possibility is that the fields themselves might vary across different universes. In some regions of the multiverse, the Higgs field, the field responsible for giving particles mass, might take on different values, leading to entirely different physical laws. Imagine a universe where the Higgs field is stronger, making particles so heavy that atoms could never form, or one where it's weaker, allowing for a universe filled with lightweight, fast-moving particles. These variations aren't just hypothetical, they're natural outcomes of the mathematics of quantum field theory, offering a glimpse into the infinite possibilities of the multiverse. As we delve deeper into these ideas, it's worth noting that quantum field theory doesn't just support the multiverse, it challenges us to think about reality in a new way. If the quantum vacuum can give rise to universes, does that mean the multiverse is constantly bubbling with new realities? And if so, what does that mean for our understanding of time, space, and existence itself? These questions push the boundaries of both physics and philosophy, inviting us to explore the cosmos in ways we never thought possible. But quantum field theory isn't the only lens through which to view the multiverse. As we'll see next, the story takes an even grander turn when we connect the multiverse to the history and future of the cosmos itself. How does the multiverse fit into the larger narrative of cosmology, and what clues might the universe hold about the existence of other worlds? Let's dive in and explore. What happens when the multiverse meets the ultimate question? How does the universe end? For centuries, scientists and philosophers have pondered the fate of the cosmos. Will it expand forever into cold, dark emptiness, collapse back in on itself, or meet some other dramatic conclusion? But if the multiverse exists, the answer might not be as straightforward as we think. Instead of a single, universal ending, there could be as many outcomes as there are universes. Some might face a heat death, where entropy wins and all energy dissipates into an eternal, frozen stillness. Others might experience a big crunch, collapsing back into a singularity, only to potentially spark another big bang. And then there are universes where the rules are so different that their fates are beyond our imagination. Cosmologists like Brian Greene have explored how the multiverse could reshape our understanding of cosmic destiny. In his work, Greene suggests that the laws governing each universe, its constants, forces, and dimensions determine not just how it evolves but how it ends. For example, a universe with a higher density of dark energy might expand so rapidly that it tears itself apart in a big rip. Another universe with weaker gravity might never form galaxies or stars in the first place, doomed to a life of cosmic monotony. In this view, the multiverse isn't just a collection of worlds, it's a tapestry of endings, each one as unique as the universe itself. But what does this mean for our universe? If the multiverse is real, does it make our fate feel less significant, knowing that somewhere out there, other universes are meeting very different ends? Or does it deepen the mystery, hinting that the cosmos is far more complex and interconnected than we ever realized? These are questions that push us to think beyond the boundaries of our own universe, imagining a reality where even the end is just one chapter in a much larger story. As we grapple with these ideas, it's worth noting that the multiverse doesn't just challenge our understanding of the universe's end, it also invites us to rethink its beginning. If every universe has its own unique destiny, does that mean each one also has its own unique origin? Could the Big Bang be just one of countless cosmic births, each one setting the stage for a different kind of ending? This cyclical view of the multiverse, where universes are born, evolve, and die in an endless dance, offers a profound perspective on the nature of existence. But the multiverse isn't just about physics and cosmology. It's also a lens through which we can examine the most fundamental aspects of human experience. What happens when we bring consciousness into the equation? How does the multiverse shape our understanding of who we are and what it means to exist? That's where our journey takes us next, as we explore the intersection of the multiverse and the human mind. What if the key to unlocking the multiverse lies not in telescopes or particle colliders, but within our own minds? Human consciousness, the very thing that allows us to perceive, question, and explore, might play a far more profound role in the cosmos than we ever imagined. Some scientists and philosophers argue that consciousness isn't just a byproduct of the brain. It could be a fundamental feature of reality itself, intricately tied to the fabric of the multiverse. This idea doesn't just challenge our understanding of the universe, it redefines our place within it. At the heart of this exploration is the work of physicist Roger Penrose and anesthesiologist Stuart Hameroff. Together, they've proposed a radical theory called orchestrated objective reduction, or ORCH, which suggests that consciousness arises from quantum processes in the brain. According to this theory, tiny structures called microtubules found within neurons could be the site of quantum computations that give rise to our subjective experience. But here's where it gets truly fascinating. Penrose and Hameroff argue that these quantum processes might not be isolated to the brain. Instead, they could be connected to the larger quantum fabric of the universe and, by extension, the multiverse. In this view, consciousness isn't just a local phenomenon. It's a gateway to exploring parallel realities. Imagine this: every time you make a decision, your brain's quantum computations could be interacting with the multiverse, subtly influencing which reality you experience. It's a bit like tuning a radio to different frequencies, except instead of stations, you're selecting between alternate versions of reality. This idea echoes the many worlds interpretation of quantum mechanics, where every possible outcome of a quantum event exists in its own universe. But in this framework, consciousness isn't just a passive observer, it's an active participant, shaping the reality we perceive. Of course, this isn't without controversy. Critics argue that the brain is too warm and chaotic for delicate quantum processes to occur. Others question whether consciousness can truly be reduced to quantum mechanics. But for Penrose and Hameroff, the connection between consciousness and the multiverse is too compelling to ignore. It's a bold reimagining of reality, one that places human awareness at the center of the cosmic story. This idea also raises profound questions about free will and identity. If consciousness is intertwined with the multiverse, does that mean our choices create new realities? Or are we simply experiencing one thread of an infinite tapestry, with other versions of ourselves living out alternate paths? These questions blur the line between science and philosophy, inviting us to rethink not just the nature of reality, but the nature of ourselves. As we delve deeper into the mysteries of consciousness and the multiverse, one thing becomes clear: the boundaries between the observer and the observed are more fluid than we ever imagined. And if our awareness truly is a key to understanding parallel realities, then the multiverse isn't just a scientific concept, it's a deeply personal one. But to fully grasp how consciousness fits into the multiverse, we need to zoom in even further to the strange and wonderful world of quantum mechanics. That's where our journey takes us next, as we explore how the tiniest particles might reveal the biggest truths about the cosmos. Quantum mechanics has long been the realm of the bizarre and the counterintuitive, where particles can exist in multiple states at once, and the act of observation seems to shape reality itself. But what if this weirdness isn't just a quirk of the microscopic world? What if it's a window into something far grander, a multiverse teeming with parallel realities? This is where quantum mechanics and the multiverse collide, offering a framework that challenges our understanding of existence itself. At the heart of this idea is Hugh Everett's many worlds interpretation, one of the most provocative theories in modern physics. Everett proposed that every time a quantum event occurs, say, a particle deciding whether to spin up or down, it doesn't just choose one path. Instead, the universe splits, creating a branching reality where every possible outcome happens. Picture a tree with infinite branches, each one representing a new universe born from a different quantum decision. In one branch, the particle spins up, in another, it spins down. And somewhere out there, a version of you exists for every possible outcome of every quantum event. It's a staggering idea, but one that solves some of the biggest puzzles in quantum mechanics, like the mysterious collapse of the wave function and the role of the observer. But how does this connect to the multiverse? If every quantum event spawns a new universe, then the cosmos isn't just a single, static entity. It's a dynamic, ever-expanding network of realities. This means that the weirdness of quantum mechanics might not be a bug in the system. It could be a feature revealing the hidden structure of a much larger multiverse. For example, the famous double-slit experiment, where particles behave like waves until observed, could be explained by the idea that every possible path a particle might take exists in its own universe. The interference patterns we see might not just be a quantum quirk. They could be echoes of parallel realities, overlapping and interacting in ways we can't fully grasp. Of course, not everyone is convinced. Critics argue that the many worlds interpretation, while elegant, is untestable. After all, how could we ever observe these other universes? But supporters like physicist David Deutsch have pointed out that the math behind quantum mechanics aligns remarkably well with the idea of a branching multiverse. And while we might not be able to visit these other worlds, their existence could explain phenomena that are otherwise baffling, like quantum entanglement, where particles seem to communicate instantaneously across vast distances. Could this spooky action at a distance be evidence of a deeper connection between universes? It's a tantalizing possibility, and one that continues to drive research in both quantum mechanics and cosmology. As we explore these ideas, it's worth noting that quantum mechanics doesn't just support the multiverse, it reshapes how we think about reality itself. If every quantum event creates new universes, then the cosmos is far more dynamic and interconnected than we ever imagined. But this isn't just a story about particles and probabilities. It's a story about the fabric of existence and how the tiniest events might ripple across a multiverse of possibilities. And as we'll see next, this quantum framework isn't just confined to the microscopic world. It's deeply connected to the grand narrative of cosmology, where the multiverse takes on an even larger scale. Ready to zoom out and explore how the multiverse fits into the history and future of the universe? Let's dive in. What if the search for extraterrestrial life isn't limited to our universe? What if, somewhere in the vast multiverse, life exists in forms so alien, so unimaginable, that they defy everything we know about biology, chemistry, and even physics? This is where the multiverse collides with one of humanity's most profound questions. Are we alone? If the multiverse exists, it doesn't just expand the boundaries of reality, it redefines the very conditions under which life could exist. And it challenges us to think beyond the familiar rules of our own universe in the search for extraterrestrial life. Take the work of astrobiologists like Frank Drake, who famously developed the Drake equation to estimate the number of civilizations in our galaxy capable of communicating with us. While the equation is a powerful tool for thinking about life in our universe, the multiverse opens up an even broader canvas. In a multiverse, the constants of nature, like the strength of gravity or the charge of an electron, aren't fixed. They vary from universe to universe, creating environments where life might emerge in ways we can't even fathom. Imagine a universe where silicon, not carbon, forms the backbone of life, or where ammonia replaces water as the solvent for biochemical reactions. These aren't just speculative ideas, they're possibilities that astrobiologists are actively exploring, even within the constraints of our own universe. But the multiverse doesn't just change how we think about the ingredients for life. It also reshapes our understanding of its potential forms. In a universe with stronger gravity, for example, life might evolve to be compact and sturdy, built to withstand crushing forces. In another, where electromagnetism is weaker, life could exist as energy-based beings, untethered by the limitations of physical bodies. These possibilities aren't just science fiction, they're grounded in the idea that life adapts to its environment, no matter how extreme or unfamiliar. The multiverse suggests that the diversity of life is as infinite as the universes themselves, each one shaped by its own unique set of physical laws. Frank Drake's work reminds us that the search for extraterrestrial life is as much about imagination as it is about science. The multiverse takes this a step further, inviting us to imagine life not just on distant planets but in distant realities. What if the conditions for life aren't rare or special, but simply one of countless possibilities in an infinite cosmic landscape? This shift in perspective doesn't just expand the scope of astrobiology, it challenges us to rethink what it means to be alive. And as we push the boundaries of our understanding, we might just find that life is far more diverse, resilient, and extraordinary than we ever imagined. As we wrap up this exploration of the multiverse, it's worth reflecting on how far we've come. From the origins of the universe to the quantum fabric of reality, from black holes to the mysteries of consciousness, the multiverse isn't just a scientific idea. It's a lens through which we can examine the deepest questions about existence. And as we'll see in the final section, the journey doesn't end here. The multiverse is more than a theory, it's an invitation to explore, to question, and to wonder. So let's bring it all together and see what this cosmic tapestry means for us, for science, and for the future of our understanding. As we come to the end of this journey through the multiverse, it's worth taking a moment to reflect on the staggering ideas we've explored. From the earliest speculative musings of ancient philosophers to the cutting-edge theories of modern physics, the concept of multiple universes has evolved from science fiction to a serious scientific possibility. We've seen how quantum mechanics, inflationary cosmology, and string theory all point toward the existence of a multiverse, a vast, interconnected web of realities, each with its own unique set of physical laws and constants. The evidence might still be indirect, but the sheer number of theories and observations supporting the multiverse is impossible to ignore. Whether it's the fine-tuning of our universe, the strange behavior of particles at the quantum level, or the subtle anomalies in the cosmic microwave background, the clues are mounting. The multiverse isn't just a wild idea anymore. It's a framework that could help us answer some of the biggest questions in science. Beyond the science, the multiverse challenges us to rethink what it means to exist. If there are infinite versions of reality, each one shaped by different choices and physical laws, what does that mean for our understanding of identity, free will, and even morality? These aren't just abstract questions, they touch on the very core of who we are and how we see the world. The multiverse forces us to confront the possibility that our universe is just one thread in an infinite cosmic tapestry, where every possible outcome, every path not taken, exists somewhere. It's a humbling thought, but also an inspiring one, reminding us that the cosmos is far more vast and mysterious than we ever imagined. And let's not forget the cultural and philosophical implications. The multiverse has captured the imagination of storytellers, artists, and thinkers for centuries, offering a canvas for exploring alternate histories, parallel lives, and the infinite possibilities of existence. From ancient myths to modern blockbusters, the idea of multiple worlds resonates deeply with our curiosity and creativity. It's a reminder that science and imagination aren't opposites, they're partners in the quest to understand the universe. So, where does this leave us? If the multiverse is real, what does that mean for our place in the cosmos? Are we just one of countless versions of ourselves living out infinite possibilities? Or does the existence of other universes make our choices and our lives even more meaningful? These are questions that don't have easy answers, but they invite us to think bigger, to explore further, and to keep asking the kind of questions that push the boundaries of knowledge. What do you think? Does the multiverse feel like science or speculation to you? How does the idea of infinite realities shape your view of the universe and your place in it? Share your thoughts in the comments below, and don't forget to subscribe for more deep dives into the universe's greatest mysteries. The multiverse might be a vast and complex idea, but it's one that reminds us how much there is still to discover. Thanks for joining me on this journey. I can't wait to explore the next cosmic frontier.